second to open the right screens. Okay. Okay. Right. We share. Right. So today, the lecture is called More on Monads. And today we will learn how to actually custom build monads, basically combine features that you want from your monad and then easily construct one that has those features, which is very nice. Okay, so goals are to first briefly revisit monads, just as a reminder, introduce 2 or 3 more, and then talk about what I just said, how to combine monads to basically get a monad that combines the effects of other monads. Okay, so this is just a reminder of the class hierarchy. So at the bottom we have functor, which gives us fmap. So given function from A to B, we can fmap to get something from FA to FB. And that is a very important class in Haskell, and a lot of types or type constructors are functors. Then we have applicative, which allows us to basically embed a pure value type A into this applicative context FA. And we have this app operator or diamond operator or whatever, a star, with this shape. So basically an effectful function and an effectful argument give you an effectful result. And we have seen plenty of examples how this is very useful and allows you to write like monadic expressions or applicative expressions in a very nice, concise, compact style. And finally, monad, where we have return, which is normally the same as pure. And then the bind. So given an effectful computation that results in an A and a continuation that takes an A and gives effectful computation resulting in a B, we can bind the one to the other and get an effectful computation that results in a B. And normally all you have to implement to define your own monad is pure and bind, and then fmap and app return have default implementations. So return is just pure, and for app and fmap, there's this lift m and app in the control monad package or module. Okay, and we have laws. So I think I shouldn't dwell on them too much, but for functor, it's that fmapping the identity is the identity, and it behaves well with composition. So fmapping the composition of 2 functions is the same as the composition of the fmaps. For applicative, I'm not sure we have seen those laws when we talked about applicative, so I just show it briefly. So the first one is basically also an like identity law for pure, and or the first 3 actually. Yeah, so I think it's not very important. And finally, monad. The first 2 are basically saying that return is like an identity element for bind, and the second one is something like associativity for bind. And I mentioned last time when we talked about the Kleisli category of a monad, that if you put monads in that form, so instead of just looking at MA, if you look at these Kleisli arrows A to MB, then those laws become very nice and symmetrical. Then they just mean that return is the identity in the Kleisli category, like identity, yeah. And this is then really associativity. But basically it just means that these things behave as one would intuitively think they behave. Okay, and we have seen examples, lots of examples. So we have, I think the very first example when I introduced monads was maybe. So you can think of the effect as throwing exceptions, but without error message. We also have either E, which is very similar to maybe, also throwing exceptions. But in addition, it also allows you to have like error messages. Whereas maybe just fails, either E can carry error information of type E. Then we have list, which has the effect of indeterminism. So one computation can have several results or no result. State S for modifiable state of type S. So we can get the state to get an S, and we can put a new state, update the state. Then IO, which is special in Haskell because all the others, or maybe except SPM, basically most of the others can be implemented just as a library, so they don't have to be built in. But IO is like deep magic built into Haskell. And it allows Haskell, even though it's pure functional programming language, to interact with the outside world via real world side effects. Then we have STM, which I suppose is also built in, these software transactional memory, which allows very high level dealing with like threads and thread synchronization in Haskell. Then we have Gen, the generator for quick check, used by quick check, basically to generate random arbitrary values. And we also had in the lectures on parsing, we came up with this parser T monad, which parses streams of tokens of type T. So normally that will be character, the T, but I mentioned that one could also, if it's like a bit, for example, one could also use this to parse binary data. And in addition to those things being monads, all of them or most of them come with like special, I mean, these things, I mean, it's just monad. And then we said one of the biggest advantages of this monad abstraction is that then you can define functions that work on every monad. So we have used mapm and form and sequence and those things. And liftm, they just work for every monad. So it's very useful. You only have to remember them once and not for each of those monads separately. But then, of course, these monads are also different. So we also have specific or special operations that only work for one of those. So for example, as I mentioned before, for state, we have get and put. So get looks up the state, and put takes a new value for the state and then updates the state. Or for either, we have this throw error to actually throw an error message of type E, and catch error. And I'm actually not sure whether I've implemented that. So maybe we should start to have some practical part to also start with to implement this. So the idea is one has like a computation that can fail with an error message of type E, and a handler. And the handler takes an E and then says what to do in this case. And the idea, of course, is if this first computation succeeds, so we get an A, then we ignore the handler and just return the A. But if it fails with an E, then we apply this handler and do whatever the handler says. So, I mean, maybe we should implement, I think I didn't implement that, so maybe we should, just as a reminder. So I again have like code for an empty project at the moment. Let me just open the REPL. And I mean, we know, I mean, the monad instance is built in. So if I ask for information on either, we have that in the base libraries that it's a monad instance. But I think throw error and catch error are not, I mean, there are libraries where they are defined, but it's not in the base libraries. So let's do this. So throw error takes an error message E and gives gives us a result in the either E monad of an arbitrary type. And of course, I mean, it's the only way there's only one possible way we can do. I mean, either is either left or right. if we wanted to use the right constructor, we would need an A, but we don't know anything about A, so we can't conjure an A out of thin air. So the only way we can do this is using the left constructor, and then we need an E, but we have been given an E. So throw error is just a synonym for left. Catch error is a bit more interesting. So what was it? It takes a computation of type A and an exception handler given error message also to either E, and then we get an either EA. And what I said in words before, handler, we just, or actually we can do this with two. So if it's a left E, then I just apply the handler to the E to get my final result. And if it's a right A, then I ignore the handler and just, I mean, I could say pure A now. I can also make it more explicit and do right A, because for the either monad, pure is return yes. Was that question?
No.
Okay. Right. So maybe we should have some sort of example. For example, we could do, I don't know, save or checked divide or something, division or diff. Or excuse me, I must just, please excuse me for 2 minutes. I must just open the door. I'm sorry about that. Just give me 1 second, please. I'll be back in 1 minute. Sorry.
Yes, there.
I'm back. Sorry about that. So for example, you could do int either string int and so I just want to divide x by y, but I want to basically give an error message if y is 0. So I could do it like this. So if y is 0, then it's throw error division by 0, for example, and otherwise just pure diff xy. Okay, I mean, this is, could do this. We can try it out, of course. So if I have check diff, I know 24.8, it gives me right 3. But if I try to divide by 0, it gives me this error. Okay, so far so good. And now I could also I mean, use this catch error. So for example, I could do checked diff prime int either string. Let's first say int, and in the case, and now that I just want to demonstrate this this catch error. So xy catch error. So I do the original thing, check diff xy, but now a handler. So if I get an error message, for example, I could just return 0. So if I do this, So if I do check diff prime 24.8, I get 3 again. So in this case, this didn't result in an exception. If I do 24.0, so now this time I don't get an exception. I get a write again because the error, the catch error caught the exception and returned 0. And of course, 0 is maybe bad. Sorry. I mean, sort of. So better would be something like maybe int. Sorry, let me leave this as is. Wanted to modify this one. Okay, so now the problem is, of course, that the original computation check diff xy gives an int and not a maybe int. So, but I can just compose it with the, sorry, no, I can't. With I must fmap just over it. And now here 0 is not of type maybe int, so now I can change that to pure nothing, for example. And if I reload again, so in the case it works, I get a just 3. And if I divide by 0, I would get nothing. Yes, that's just as a demonstration how to use this catch error and how to implement it, because I think I didn't do that last time. Please feel free to interrupt me if there are any questions.
Yeah, no, not so far.
Okay, thank you, Karina. Okay, and now let's look at 2 or 3 more monads that I already mentioned in passing before. I mean, okay, first of all, identity. I mean, we have already talked about that, and we used it for our optics at certain places. So identity is basically the monad that doesn't have any special effects. So it's just a monad. I mean, the monad instance is trivial. So return is just the new type constructor, and bind just basically function application. And we already saw that it's useful for like optics. So sometimes we just used it for the applicative. I think until now we haven't. Oh yeah, actually I gave an example. I remember. So basically the identity monad would allow you to write pure code with do notation. Because it's a monad, you can use do notation, and then at the end you can just unwrap it. So just as a reminder, I mean, you can do stuff like, I don't know, 42. 42. So you could do run identity. Okay, and you must import that, but that happened automatically here now. I mean, something like 6, just to demonstrate that you can use do notation. It's a stupid example, but nevertheless, so yeah, I mean, there's no good reason to do this, but I mean, you could. So yeah, that's the identity monad. And so we will see other uses, except for in optics for this later today. And then there's something called reader, and I think I've mentioned that before. And it's similar to the state monad. So we have state, but I mean, the difference to the state monad, it's read-only state, hence the name reader. So it can read from state of type R, but it can't modify that state. Let me just check what's here. Right. So I mean, this is defined here in a similar way, but for now, let's just give our own definition. So new type reader. So R is the state type. That's traditionally called run reader. And given the state type, it allows us to compute a result. And pure. So we need an instance functor reader R. We need applicative, and we need monad. So we can just use the boilerplate here again. So fmap is just lift m. If I import this, okay, need this instance sig. Okay, and applicative, so pure. So given an A, we must be able to produce a reader RA. So what should pure A be? So the reader constructor, and now given some read-only state, we must produce an A here. And because we don't know anything about R, and we must produce an A, the only thing we can possibly do is use the A we have been given, which means we ignore the state. So we could also write const A. This is again an example of something where there is no choice. I mean, this is the only possible implementation for a function with the signature. But it also fits well with what I said before. I mean, when I tried to give you some intuition for pure, I said I mean, these monads, you can think of them as effectful computations where the effect depends on the monad. And I said pure is basic. And it's always important to remember, I mean, an effectful computation means you potentially can use the effect, but you don't have to use the effect. And pure is basically a way to produce a result without using the effect. So now in the case of reader R, the effect is that you have access to some read-only state of type R. So not using this effect means ignoring the state. So given an A, you ignore the state and just return the A. So I hope that makes sense. And now for this app operator, so reader R A to B, reader R A, reader R B. We just use the standard implementation. Okay, and here for return, we also use the standard implementation that it's just pure. Okay, and the most interesting thing for most monads is always the bind. Everything else is more or less boilerplate, except, I mean, the pure is also. So the bind, giving a reader RA, and the continuation from A to reader RB, and to produce a reader RB. Okay, so we have something type reader RA and a continuation, and we want to produce a reader. So I need the reader constructor, and I have given some read-only state, and I must produce a B now. Okay, so I mean, what I have is this M. I mean, obviously, in order to produce a B, I must somehow use this function here, the continuation, applied to an A. So first I need an A. And so how do I get an A? Well, I have this reader RA, which gives me an A for a specific value of the read-only state. Now I have a specific value, so I can use that one. So I can do run reader MR. So this is now of type A. So I can apply the continuation to this. So this is now of type reader RB. Right, and that's already it. Yeah, I think that's already it.
Yeah.
Oh,
In the
I
beginning,
must, sorry. I mean, I need a B. So now I have something of type reader RB, but because I'm using the constructor here, I need a B. So now I must somehow get to this B. That means I must run this thing as well. And I must supply some R, and there's only one R I possibly have. But there's the symbol is wrong. Okay, I mean, that's again basically the only thing I can possibly do. And so that's that. And I mean, for the state monad, we had get and put to get the state and put the state again. I mean, update the state. Now, because for the reader monad, we have immutable state, I mean, read-only state. There won't be anything like put, but we, of course, want to be able to get the state. However, for the reader monad, traditionally, it's not called get, it's called ask. So we can implement ask, which gives us the state. So it's of type reader RR. So reader. So given a state, we want to produce an R. Well, obviously, the only possible thing we can do is, I mean, and that's what we want. We want to look up the state and give it. And of course, this is just an identity function. And finally, there's something, even though you can't update the state, you can locally update it. So you can have a subcomputation that uses a modified state. So that's called local. And it takes a function from R to R. I think, let me just check that I don't get that right. Wrong, I mean, that I don't get it wrong. Okay. So it basically gets a update function and something of reader RA and produces an updated reader RA, which then you basically uses a modified state. So local F M reader. So given state, I run the given computation, but not for the given state, but for the modified state. Run reader. No, not run reader.
Yeah, it's
Run
the
reader. Yeah,
error.
yeah, yeah. Yeah, thanks. Just so. Okay. Right. Maybe some example computations in reader just to see. Let me see. Just 1 second. Right. Yeah, probably a silly example, but I mean, normally reader is used for like configure. I mean, or typical use case for reader is if you have some configuration data for your application, some config file that you pass. I mean, maybe JSON or whatever. So you have some configuration data, for example, the location of the log file or some flags, whatever. And then, I mean, typically in an imperative language, one way would be that you use a global variable that carries this, it has the value of this configuration data. And then from everywhere, because it's a global variable, you can have access to it. But of course, we don't do global variables in Haskell. And if you don't use a global variable, then the alternative would be you have to pass it on to all locations where you need it. And that's, of course, a bit tedious. I'm just trying to think of a good example. For pure reader, let me think. Just trying to something that makes sense. I mean, we could, of course, come up with some arbitrary value, but okay, fine. Maybe precision or something. So right. I mean, so let's say, I mean, first of all, I was just checking. I'm sure there is some better function, but I mean, we could do something like, I mean, it's not just an example. So let's call it round prime or something. So given let's say given a number of digits and a double, it gives us a double rounded to this number of digits. Digits x. And I mean, we do have like the usual functions, floor and ceiling and so on. So one way to do that is to multiply x with 10 to the power of digits, add 0.5, floor this, and divide by 10 to digits again. Why is floor complaining? Ah, right, because floor gives me an integer, so I must do from integral. And now, right. I want to say that this is again a double. Right. I mean, this is not important. It has nothing to do with monads. It's just, I just want an example. I hope that actually works. So let's see if I have a pi. So round prime pi to 0 did.
Tiene relote.
Sorry. Oh, something was messed up for whatever reason. Good error. Oh, I don't know what
Please
happened.
duplicate the wrong. Yeah.
Yeah, thanks, Karina. I don't know. What else?
I'm missing the final parentheses. Yeah.
Now it should be fine. I'm sure there's somewhere in the libraries there is a function for to do this, but I forgot the name. So anyway, so let's try this, whether it works. So if I have round pi to other way around. So okay, so to 0 digits, it's this, to 1, 2, 3, 6 or something. Okay, I think it's good enough. I mean, it's not important. It's just an example. But you could imagine that you have some config. I mean, you have some sort of numeric application and you want to always round to, this is like the number of significant digits. So you have something like data config, and normally it would have like the location of a log file and whatever, but you also have sig digits of type int. Okay, and now the idea is I mean, you have this numeric application and you want to do various operations, but you want to take this into account. And I mean, for example, let's say you have my div or something. So given a config and 2 doubles, gives you a double, and my div config xy is round prime config significant digits config x divided by y, for example. And this is complaining because it could be a new type, because it only has one field. Anyway, and now we could have something else. What can I say? For example, my reciprocal value config double. So recip config x is my diff config 1x. What is this? Oh yeah, okay, fine. Okay, something like this. And I mean, this works, of course. I can do my recip config, I don't know, 4, 7. And I would get 1/7 to 4 significant digits. So far, so good. But you can imagine, I mean, this is a small example, but basically all your functions, I mean, you always have this config argument that you have to pass around. And even, I mean, for example, I mean, you could have something like recips config list of doubles recips config access is map my recip config over the list. So the point I'm trying to make, I probably shouldn't waste that much time on this, but anyway, so recips config 4, 1, 2, 3, 4. Right. So the point I'm trying to make is if you have something like that, that's typical, so you have some configuration data that is like global for your application, then basically you pollute all your functions with this. So basically all the functions have to take this config as an argument and then pass it on to other functions. So that's quite a typical situation. So if you don't use like something like a global variable for this, then you have to do it like this in a functional program. So we always have to pass this configuration around. And of course, there's nothing wrong with that per se, but it's nevertheless somewhat noisy. And you always have to, I mean, all the functions in your code basically have this config argument. And this is typically, I mean, one use case for reader. So you would then, I mean, do something like type my monad or M or whatever. M is reader config. And then you could have, so for example, let me now use this suffix M just to indicate that's in a monad. So that would be then double M double. So around MX would just be do we ask for the configuration, then we apply this round prime that we have. Okay, it takes the config 6 digits config and the X, and that's the result of this. So this is arguably more complicated than it was before. I don't know. But anyway, now the other ones are nicer because now I, for example, this my diff. So my diff M would now just be double to M double. So my diff M X Y, sorry, it says 2 doubles, this one. XY would now just be round M X divided by Y. And now this my recip M just be my diff 1x. Complaining now.
Double, no?
Oh, my diff m, sorry. Yeah. And finally, recips m just, I mean, one way to write it would be map m my recip. Right, and I mean, it should behave the same, of course. So now if I want to replicate this example, so it would be recips m, so run reader, recips m, this list, config, what was it for? Right. So I mean, somehow now the functions looks much cleaner. So we have this monad now, but I mean, in application code, like real world application code, you will have a monad anyway, like IO. So this doesn't make it worse. And basically you hide this stuff where you need the config file in one function. In this case, this round m. And then the others can just use this, and the config itself doesn't explicitly appear anymore. So in particular, you don't need this extra argument all the time, because this is now taken care of by the monad m. So that's exactly what m does. It basically keeps this value config available for anybody that needs it. And when somebody needs it, he can just ask for it. Okay, this is maybe not completely convincing, so it will be more convincing by the end of today when we know how to combine monads, because often this reader is not used in isolation, it's just used in combination with other effects, for example, with IO. The typical pattern would be to combine reader with IO, and then in your main program, as the first step, read the config file, pass it as your config value, and then the rest of your application would be basically in a monad that we will like understand today, that would combine IO and reader, and then everywhere in your, then it's almost like a global variable, except that you can't modify it. Oh yeah, and I should also just as an example, what this local is good for. So maybe we could do something like with double precision. So mx or a with double precision is local. So given a config, we use config what was it called? Config sig digits is 2 times config sig digits config. Right. We can try this as well, whether this works. So double precision. So now instead of 4 digits, it should use 8 digits. So locally, we can basically modify the local state. I mean, in this case, it was globally because I applied it globally to the whole thing. But I mean, I could also, of course, I don't have to do that. I mean, it could also be, I could use it somewhere in between. Right. So that's that. That's just another example for monad. Very useful one. I mean, reader is arguably maybe the most important, almost, I mean, I think it's one of the most important ones, the most commonly used ones, because this is such a common requirement that you have a bunch of data of state, read-only configuration data or something, and you need it at all sorts of places in your application. So reader is very useful. And actually, we can also simplify this. I mean, we had this U-type reader, run reader to wrap and unwrap. but we could also just use functions themselves. And I mentioned that last time, I think, when I talked about profunctors. I told you, or I showed you what happens if you ask for information on the function arrow. And we saw in particular, it's a monad. And that is actually this monad. So return is just constantly returning X or pure, and bind is this. And if you compare that with how we implemented run reader, it's exactly the same, except we don't wrap and unwrap with these new type constructors. So if you don't have this reader, and if you don't have this run reader, basically just have R goes to M F of R, and that's exactly this, except that instead of F, it's M, it's called G here. So that means, and that is incidentally, I think I shouldn't type that in now, because that is exactly the definition given in the base libraries. So we can basically do exactly the same thing without this new type constructor, just using functions. So, I mean, simply, I mean, a function that can use read-only state of type R, or in fact, for computation, is basically just a function from R to A. And I mean, one could do this. Right. Okay, so that's already in the base libraries. And now, of course, the question is, do we also have ask and local? So we would, I mean, somehow we want, the idea is, I mean, this reader monad and actually this function array monad, they are very similar. The only difference is this new type wrapper and unwrapper, but they behave the same, and basically intuitively they do the same thing. So we should also be able to implement something like ask and local. I mean, actually we can do this if I mean, here's ask and local for reader. I could also have like ask prime for R to R. And this would then just be it. And I could have local prime R to R, R to A, R to A. Local prime F M is, and I basically use exactly the same definition as here. I just don't have this new type stuff. Oh yeah, fine. In this case, I can write it easier like this. Right. And of course, that's sort of not nice. I mean, what we would like is to define it once and for all, and not have basically one version per monad. Actually, we can give a third example. Let me just check on the slides that I don't diverge too much. Okay. Right. So the idea somehow now is, I mean, these monads are very similar. So we have the explicit reader monad, and we have basically the arrow monad, not sure what to call it. Maybe function, I mean, it's functions that start in some fixed type R. And I mean, those two monads behave very similarly. I mean, the only difference is the one is wrapped in a new type. So things like this ask and local, we would ideally not have like different versions for that, but just one ask function and one local function that works for both. And I mean, if you remember, recall back while the first week of the class, we talked about ad hoc or parametric polymorphism and ad hoc polymorphism type classes. I mean, this screams for a type class. So we would need some sort of type class that has this ask and local functions or methods. And then the idea would be that both reader R and functions from R are instances of this class, and we have ask and local. And then So it's this class. So the next challenge is we want to implement this class. And the name traditionally is monad reader. So that's the name of the class. And the first attempt might be something like this. So we have ask. And now, of course, I'll get into trouble because I have, but let's see. Probably have to comment stuff. So ask should be type MR and local. If I have a function to modify my state. Now it's complaining. Okay. Let me just comment everything for the time being. Okay. And I mean that looks reasonable, I suppose. So we can try to what I commented here to our so we can now try to make instances. Monad reader reader R. And we also want to make these functions. So that would be written like this. Okay. Now we can, for example, try to implement ask. We can just take the definition from here and put it there. Right. And now we get an error. It says couldn't match type R1 with R. So that looks a bit strange. But maybe here this hint that the editor gives me. I mean, where does this R1 and R2 come from? So the problem is that even though I call it R here and R here, there's no connection between this R and this R. And incidentally, what this signature means, I mean, there is no R here anywhere. So this R is like a free type variable. So that means ask would allow me to produce something of type MR for every possible R, which of course it's not true. I mean, the actual ask that I want can't give me an arbitrary value. It just can give me a value of type R of the type I'm using here. Right, so that can't possibly work. So okay, so that can't work. I get type errors for local as well. I would get right. So one solution is to instead use higher kinds. So I mean, reader R is of type star to star. It takes an A. I mean, yeah, like this M here. So reader R A. So it's actually reader is, let's see. I mean, if I ask for, let me comment this quickly, or the whole thing. So if I ask for the kind of reader, of course it's star to star to star, because it takes the type of local state and the result type to give me a type. So, but this M here is of kind star to star. I supplied just with the result type. So there are, that's why I wanted to write an instance for reader R, not for reader R. I mean, we have seen that many times before. But of course, one thing I could do is change my class monad reader so that now this M is instead of type or of kind star to star to star. So I can make that explicit. I think I need some sort of extension for that, kind signatures, okay. And this is a warning. So they suggest to not use the star. But anyway, I can leave that for now. Right, so then of course, this is no longer type correct. Now I must supply both parameters. So ask now should be of type MRR. So the first parameter is the type of state. The second parameter is the result type. So ask is then of type MRR, and local needs this state type here. So now I can actually write this. No, I mean the class I can write, and now it's not reader R any longer. It's just reader. So now actually I can use this, and I should also be able to use local. Okay, and that compiles. And now I could do the same here and hopefully copy these definitions here. Of course, it's not prime anymore. Okay, so that would be one solution that actually works. So by making it higher kinded, this class, I mean the M type parameters, the type of state and the type of results, I can actually pull this off. So let me see. So this is the solution one on the slides. One thing we now can't really do is, I mean, we actually would like to, I mean, the name already suggests monad reader. I mean, this M is supposed to be a monad. So actually we would like to write something like a superclass that it's monad, that M must be a monad. But this now doesn't work anymore because this is now the wrong kind. I mean, because a monad is something of kind star to star. It takes one type parameter, not two. So this is one disadvantage of doing it like this. Actually, there are modern extensions where I could basically fix that, but nevertheless, it's not ideal. And there's another option. There's something now new that you haven't seen, and that is that, I mean, so far, all the classes that we have seen always had one parameter. So it was for the show A or eq A or monad M or functor F or applicative F or traversable T. So always one argument. So these constraint names, the class names, always have one argument. But actually, that's not a, I mean, there is an extension to change that. So there is, I can write something like monad reader RM, so have two arguments. And then I can also give my superclass constraint. Now the signatures are as before. And now I get an error because I need an extension for this. This is called multi-param type class. Don't need the kind signatures, I think. So this is new. That allows to write classes like this, like that have more than one argument. So in this case, the R and the M. So now, of course, this is, must change this. So now the reader R. Okay, and this is also common. This is actually also mentioned on the slides, that if you activate this multi-param type classes, you often also need more extensions, flexible instances, and flexible context. And I actually don't, I mean, there are some rules that are broken by this, but you can just add that. This flexible instances, whatever it means. Right, so this instance now still compiles, and here also can write it in this form. Okay, so this is, at least it compiles. So this is a second way, and probably in this case, the better way to fix this. I mean, to write this monad reader class. Now we have two instances for that. But we will see that, yeah. Okay, and actually, not only can we have this monad superclass, we also have other advantages that that it doesn't have to be completely generic in this. So I mean, sometimes we just don't have a type constructor that allows arbitrary state types, like for reader or for arrow. So as an example, let me just also add containers. Let me reload. Let me import this. Okay, let me just see what the example here is. Okay. Okay. And let me do this example, and then we can have a break, and then we can continue afterwards. But let me just do this briefly. So the idea is we define this type synonym n for environment. It's just a map, or env-a. It's a map. Is it fa? Int. Okay, fine. Int. String int. Now new type env-r for env-error. Okay, and that's just env-r run env-r. The idea is it's either, check. So given an environment, produces either string A. Right. So we already see, or I mean, we can, sorry. We can guess, so this is sort of like a combination of reader and either. So on the one hand, we have this read-only state of type env here. On the other hand, we have this either here, so we also can do exceptions. So let's write some instances again. Always the same. So instance functor env-r where 100. But after today's lecture, you won't have to write this by hand much longer. So that's okay. So again, fmap, we normally use lift m. Pure, we must do something. But this other one, use app, and return, we use pure. Okay, so pure A. So it must use the env-r constructor. It gets an environment. Right. And now, I mean, I must produce something of type either string A. And I mean, the obvious thing to do is write A, which again makes sense. So here we basically have two effects. We can read from this read-only environment, and we can throw exceptions. So pure means we don't make use of any of those effects. So we don't look at the environment, hence const, and we don't throw an exception, hence write. So that's like what we should do. And now the bind is, of course, a combination, as always. So we have some m and a continuation. Right. Okay, given an environment, what can we do? Let me just see how this is done here. Yeah, okay. So we can do that explicitly by hand, but we can also be in the either monad now. So, I mean, either is a monad, as we know. I mean, what I can do is I run the first computation, run nfr m to get an A out, which, because of the either monad, if this throws an exception of type string, we will immediately, I mean, because of the how bind works in the either monad, this will automatically be taken care of. And now I can run nfr. I can apply my continuation to the A and apply the read-only state again. What's this? Ah, yeah, I must, of course, give the environment. Okay. Right. So this is one way to do the monad instance. And now, just because I started today's lecture with this throw error and catch error, I mean, we could implement those as well. But there actually, we have like a similar problem that we have this for either now, and we would like to have it for a monad like this as well. But in particular, we also want to make this an instance of our monad reader. So instance monad reader. So the state type in this case is env, and we have envr. So what's ask r given an env, write env. A local I still have to do, but of course I can simplify this first. Okay, and local f m. So we have envr given an env. We run the given computation, but applied to modified state. Okay, so this looks quite promising. So we can write, I mean, this class, so we can write various instances for it that are now all instances of this monad reader class. And I mean, I had this other solution earlier with the higher kinded one, where it takes two type arguments, one for the state type and one for the result type. But the remark on the slide is that, I mean, I couldn't do this here because envr only has one type argument. So it is not of the right kind because the state type is fixed to env. So in that sense, this solution with the multi-param type classes is more flexible because it works for both things like reader that have kind status star, and also things like envr, which has kind status star. Okay, so far so good. And now we can make a break, and then we will see after the break that this is not the final version that we can use. There's still a problem with this, and then we'll fix that. And then we are actually ready to look at how to combine monads. So, but let's first have a break, maybe until half past. Yeah, half past.
Yeah, I think it's good.
Okay, and talk to you in 10 minutes. Okay, should we continue?
Yeah.
Okay. Let me just now see whether I can remove the comments again. So must remove this. And now let's look at this here. I mean, I did that specifically for this monad M, which was reader config. But of course, that should work for arbitrary monad readers if the state type is of type config. So I should be able to write something like monad reader config M M RM like this. Okay, so now this other extension that we need. Right, this even seems to work. Let's see. Okay, I must do this. Okay, so far so good. Let's see. Yeah, I can do these other things as well. Reader config. Here. And here. Okay. Right, and now I should actually be able to do things like I mean I can do the example that I had before.
I think you need to save the file, Lars.
Yes, I need to save the file. Thanks, Gaina. Okay, this is gone, but I can still do run reader. What did I do with double precision? What was it? Recips M 4. Ah, 4, sorry. Must be config. Okay. So that still works, but I now could also use it for a different monad, namely, for example, this arrow monad. So I don't need this run reader. I just do this without wrapping it into this reader new type, and that also works. So I mean, this actually works. So this monad reader constraint. Now let's see. There's an example here where it doesn't work. Okay, let's try this example here. With double M is local 2 times 2 M. Okay, let's first do the hints. Right. And now we get this ambiguous type error. So I mean, I could try to write this. So with double, so given I have a monad reader, some state type R and a monad M, and let's say R is a numeric type, then it should MA to MA. Right. And I still get an ambiguity error, even though, I mean, it's clear what we want here, right? I mean, given one of these monad readers, for example, reader, some numeric type, for example, int, it should be possible to, I mean, we can, okay, fine. I mean, even if we give type arguments here, we could try R. And now we have this scope type variable problem again. So I can try to fix this. RMA and give scope type variables. Right. And somehow, even though, I mean, this is what scope type variables normally does, that it allows me to, that the type variables named in the signature are the same that I name somewhere in the body. It still gives me this weird ambiguity error that this R0 is appearing there. So, right. And the reason is that, if you remember, like when we talked about type classes, we had this example to do given a string, to first read the string as some A and then show the result. And there we also have this ambiguity error that it doesn't know. I mean, in this case, in the GHCI, it doesn't give me an error. I think here it would if I wrote this here, to string. I do shown after read, then I also get this ambiguity error. And the problem here is it doesn't know at which type I want to pass the string. And because it can't infer that from anything here. I mean, the read takes a string and passes it as an A if it can, and show takes a showable A and converts it into a string. But I mean, it can't know, GHG can't know what A I'm intending here. Do I mean int or bool or whatever? And a similar problem, so that, I mean, that we had when we talked about type classes. And the similar problem we have here. I mean, of course, we intend because the signature only mentions this M, only the monad. But it nowhere mentioned the R. So we don't know what R. I mean, we have this instant monad reader for M with state type R, but that doesn't mean that given the M, I can deduce the R. I mean, there could, for example, be several instances for the same M with different R's. So just giving the M, there's no way the compiler can infer which R I'm actually talking about. So that's the problem here. But it is a bit weird because if we look at the instance, so for example, the instance for reader R, we know what the state type is, namely this R. So given the monad, reader R, we know the R is this here. Same for functions. I mean, if we have the monad, we know what R we use, namely this one. And also same here. If we have env R, then we know the state type is env. So somehow we know, and therefore this doesn't make sense to us, or shouldn't make sense. I mean, given the monad, any of the three examples we have seen for monad reader, we know what the state type is. Given the monad, we know the state type. So the compiler should be able to deduce the state type, but it doesn't. GHG just doesn't know that. I mean, what I just said, that given this reader R, that from, if I give you the term reader R, then of course you can read off the R here and know that's that R. GHG doesn't know that. And there are actually two ways, or at least two ways to fix that. And both are actually used in in practice. We will mostly concentrate on the second one, but I'll give you the first one anyway. And this is an advanced feature, a relatively new feature called type families, or in particular, when we talked about classes, we have always seen said, okay, a class can have these methods. But in addition, class can also have something called associated types. So there the syntax is like that. So I write type, and then I can say, for example, state or whatever. I don't know what it's called in the slides. Okay, in the slide it's called env type m kind star. And now I need some yeah, okay, I need type families. Okay, and if I do it like this, so this now means part of the class definition is not only these methods. If I write an instance, I must also give this type. And in this case, if I do it like this, so this would go away. So it's just monad reader m again. And then here I would use this env type. Just give me, I'm sorry, I don't want to delete so much, so maybe I just 1 second. Let me just put this instance here as well. And now let me just copy those 4 things. Let me just comment this problematic thing for the time being. And let me just give this a new name. So monad reader prime. So the R goes away. We are back to normal type classes with just 1 parameter. But now the R this basically says, okay, if I have a monad reader, then there must be a so-called associated type that I call env type of this monad. And this is then supposed to be the state type. So instead of R having result type it now has result type env type m. Why am I getting? Okay. I should call that as prime now. Local prime env type m env type m like this. And why is this now? Because in the original definition I also have it. So let's delete it here again. Why are these things complaining? Okay, right. So now let's see whether I can use whether I can make our 3 examples instances of this. So it's now everything with prime. What now? But I did allow families. Okay. Okay, and now in the instances it's complaining. Sorry. Now it's complaining that I haven't given this in this type. So here now in my class definition, I say there must be this associated type. Now in my instances, I must also provide that type. So if I do an instance, then the syntax is like this, also type, env type, and now the m I'm defining it for. So in this case, reader R. Okay, in this case, it's R. Here, type, env type is also R. And here, type, env type, env R is env. Okay, and now this all compiles again. Okay, get this warning, but apart from that, and now let's see whether now we can implement this problematic one. Let's call it double prime. local prime. Double prime. Monad reader M prime M A. Right, and of course now I need that the nth type of M is a numeric type. Okay, and now this actually compiles. So that is one solution to this problem, using so-called associated types. So there can be one or more types. So basically the methods of a class, it's not only functions or values, it can also be types. And they are called associated types, and this is the syntax. So this would be one solution for this. And that's actually also like the more modern solution. Nevertheless, the more common solution in Haskell that has existed long before there were these associated types is something else. And so that is more like the original definition that we had here. And the point is, I mean, in our examples, as I demonstrated, if we know our M is reader R, we know the the R, because it's in the name, reader R. So that R. Same for arrows. We know the R. And also here, nth error, because there is only one, I mean, it's not polymorphic in the state. The state is always nth. So in this case, we also know the nth, the state type. And there's an extension, another extension to GHC, where you can tell GHC this. So you can tell GHC that given, if you have more than one parameters, like in this case, 2, R and M, you can tell GHC that if you know one, the other is basically determined by the first. And the syntax for this is like this. Like this. And I need another extension for that. That's called functional dependencies. So this now says, so I have a class with 2 type parameters, R and M, but for every given M, the R is fixed. So the M determines the R. And now I should also be able to write this. So I also need, let me just remove this. Okay, with double, I need num R and monad reader RM, MA. So what we originally wanted to write, basically. And this now also compiles, because now this ambiguity is gone, because now even though the signature, I mean, GHG only sees the M, but now because of this functional dependency, it knows that for this, once it knows the M, it also knows the R, and then it knows what to do. Right. And so yeah, this is the syntax. There are also, okay, and GHG also checks that. So if we try to write a different instance where the same monad has a different, then we will get an error. So if I now try to do an instance monad reader, whatever, bool env r, then I should get an error, functional dependencies conflict between instance declarations, bool env. So the compiler now makes sure that I really only define one instance. So for every given like parameter M, there can only be an instance, one instance for a specific R. So that's what these functional dependencies do. And right. So that's that. That's monad reader. And as I said, I mean, there is a famous library, MTL, monad transformer library. And that defines it like this. So there are also alternatives where this associated type class, this associated types is used. But right, so I mean, the more common solution, the traditional solution is to use these functional dependencies for this. So we have This is the definition of monad reader. And actually, this is not only for reader. I mean, there's like a pattern. So for each for many of the classes or the monads we have seen, there is like an associated type class. For example, there is one for something like either. So there is a class monad error em. That's very similar. So we also have a superclass M is a monad. And there we have these throw error given E. So it's supposed to be the class for monads M, where you have some sort of exceptions of type E. So MA and catch error. What was it? MA and the handler. Right, now it will complain that I defined that already because I started the lecture with this. So we can now change this into an instance of monad error E, either E. Now this hopefully should just compile. Why do I get an error here? Okay. Okay, and as a second example, I mean, why it's useful to have this type class. I mean, we have this this other example here, this nth error thing. So now we could also make it an instance of monad error. So instance monad error nth error where. So again, we need throw error. Sorry, we must give the type of error message, which is also a string. So throw error E. Okay, we have our nth error constructor. Given an environment, we just do left the error message. So we don't need this, it's just const. And catch, just at the signature. So catch error, M handler, nth error, given an environment. And now, I mean, I could use the, actually I can, I mean, I could use the catch error in the either monad. So maybe let's do this. So catch error. So in the, my normal computation is now run nth m nth. And my handler is now, if I get an error, then it's run nth my handler applied to the error in environment nth. Okay, so I could do this as well. So I have a second example of something that's a monad error that's not either. And I could, for example, also turn maybe into, maybe as the last example, monad error of error message type unit, maybe. So throw error of type unit to maybe a. This is just nothing. And catch error in this case. Okay, what do we have? We have a maybe a and the handler of type unit to maybe a. Maybe a. Well, that's if it's nothing, we have the error case. So we just apply the handler to the error message. And if it's just adjust, then I can ignore the handler. Okay, right. And let me just check the slides. We have this done. Right, showed you that. Showed you that. Okay, now we also talked about monad error. And there's also something for other, I mean, there are other, for a lot of the monads we have seen, there are like associated classes. So for either, we had monad error. For reader, we have monad reader. For state, there's something called monad state. Just 1 second. Oh yeah, sorry. I think I forgot the functional dependency. Yes, I remember I got this weird error here where I had to yeah, I had to give these stupid type annotations. I think that was because I forgot the functional dependency. Let's see if I add this here. So same as in the reader case, the monad determines the state. In the monad error case, the monad determines the type of error messages. I think. Go away now. Yes. Okay.
Yeah.
Yeah. Right. Okay. And then we also have monad state, again, where the monad determines the state. So monad state SM, S is the state type and the monad, and our old friends get and put are actually in this class. So it doesn't just work for the state monad itself, it works for arbitrary monad states. But the state monad, of course, is an instance of it. Then there's also something called monad IO. That's for monads, type class for monads that can do real-world side effects. IO itself, of course, is an instance. And it has this method here. So you can lift an IO action into that monad, and that's called lift IO. Right. So that's that. And now, if there are no questions, we can go to combining monads.
No questions so far.
Okay, thank you. Then let's see. And I mean, what do we mean? I mean, for example, we had this reader env. Oh, sorry, we had this env-r as an example just now. And that has somehow aspects of either string, because I mean, it's an instance of monad error string, so it can throw and catch exceptions of type string, but it's also an instance monad reader env, so it can actually read only state of type env. So it's like a combination of those two, of reader env and either string. And I'm not sure whether, Karina, maybe you know, I mean, that's one of the exercises. I'm just not sure whether you have done that already or should have done that already. So there is an exercise where you are supposed to write a monad instance for something called error state.
Yeah, yes, there are.
That's already okay. So where this env error is a combination of reader and either string, this error state is a combination of state S on either string. So that's like also a combination of two monads. So you have the effect of throwing exceptions of type string, and you have the effect of mutable state. And if you remember our definition of parsers, so that was something that takes a list of tokens and returns a list of results and unconsumed input. This is like a combination of state list of T. I mean, it looks very much like the state monad. So the original state is the list of tokens, the unconsumed tokens, and then you get a result and an updated state. But the whole thing is wrapped in a list. So it's a combination of basically the state monad and the list monad in this case. So there's indeterminism in parsers. It's like a combination of state and list. So the question is, and I mean, for all these examples, we wrote instances by hand. So I mean, we wrote, I mean, a lot of that is always boilerplate, as I said. I mean, the functor instance and applicative, and I mean, all you always you just have to implement is pure and bind. But we had to do that by hand. So for each combination, and then you can imagine we have, I mean, there are already quite a few combinations that we know. I mean, we have this either, we have reader, we have state, and already, I mean, that already gives you like, I mean, if you can combine all of them somehow, it's already like dozens of combinations, or at least 10 or so. And list, if you throw list into the mix, and IO maybe, so I mean, there are lots of combinations. So it would be tedious if you always have to write these instances by hand. So the question is, can we somehow combine two monads, for example, like here, reader and either, or here state and either, or here list and state, to automatically basically get these combined monads without having to do anything ourselves? And unfortunately, the answer is not. I mean, it's basically yes, but, or yeah. So it's not universally possible. But in these three examples, at least, and in many more, it is indeed possible. So let's first look at functors. So maybe I can try to import this. Why is this? Whatever. It seems if I have functional dependencies, I don't need multi-param type classes because that's implied automatically. I didn't use that. Okay, fine. So let me import data functor compose. Reload and ask for compose information. So compose is just a new type. It takes 3 parameters, an F, a G, and an A. And it's just a new type around F applied to GA, where F and G are basically type constructors. And the interesting instance, let's first look at this one here. So it says that if F and G are functors, then compose FG is also a functor. So functors compose nicely. If I have two functors, I can compose them, and I know the composition is again a functor, and because I have this instance here, I don't have to write the fmap by hand. So I don't know, let's look at examples. For example, I mean, two nice functors, for example, maybe and list, okay? So let's say F is list and G is maybe. So if I specialize the definition of compose to list and maybe, then this here's list of maybe A's. So for example, I could have just call it X. So a list of maybe, I don't know, strings, for example. So we have just Haskell, nothing. Just Kenya, for example. I mean, this is now a list of maybes, but if I add the compose constructor, I can ask for the type. Okay, so this is now of type compose, list, maybe, string. And now because of this instance, that if I know that list and maybe are functors, then the composition is also a functor, I should get fmap for free. So I don't know, for example, length. So we should be able to do fmap length. So I should be able to fmap length over this automatically. And indeed I do. So I mean, I'm able to. So it composes the fmaps for lists and maybes and does the right thing. So the fmap for list is the usual map, so it applies the function to every element. And the fmap for maybe is the one that applies the function to justs and leaves the nothings as nothings. And this is exactly what happens here. So we get compose just the length of Haskell, then nothing, and just the length of Kenya. So this is nice. I mean, this is as good as one could hope for. So, and I mean, it's also easy to actually implement. I'm not sure whether it's in right. I mean, it's actually, I mean, I now just imported it, but we could have written it by hand. So in order to fmap this f, I mean, compose x is f of g of x. So you just must do two fmaps. So fmap f goes from g of x to g of y, and then fmap f goes from fgx to fgy, which is exactly what one wants. So it's also easy to write. And if we look at a bit more here, we see that even if f and g are both applicative, then the composition is also applicative. So we not only is it true for functors, it's also true for applicative. So we can also apply use this for applicative. So for example, I could do pure Haskell, compose, list, maybe, string, sorry. And it does the right thing. So it first uses pure to get it into maybe. So for maybe pure is just, so I get just Haskell. And then it uses pure of just Haskell to get it into a list. And for lists, pure is singleton list with one element. So that works. And this app should also work. Let me see. For example, I could do composition. So I can do something like composition, compose, just Haskell, nothing, just Kenya, and compose, nothing, just Nairobi. Right, and it will do like the right thing, that according to the applicative instances of list and maybe. So in particular, that means it will try to pair each element from the first list with each of the second. And then if one of the two is nothing, we get a nothing. So just Haskell, nothing is nothing. Then just Haskell, just Nairobi, it gets concatenated. Then nothing, nothing is nothing, nothing, just Nairobi is nothing. Just Kenya, nothing is nothing, just Kenya, Nairobi is Kenya, Nairobi. Right. So it's also applicative, and that's also as nice as it can be. So given two arbitrary applicatives, you get an applicative easily. But unfortunately, if we look again, then we don't see the same for monad. So there are like other instances here, semigroup and monoid. But
Lars,
yes,
there are questions. So
okay.
Jason said, what's the intuition for this in the length, in the line for length?
In the length,
This
one.
yes.
Well, I mean, we have. I mean, length is a function from a string to int, right? So so this fmac length goes now from compose. I mean, can now given a function from string to int, it can now take a list of maybe strings to a list of maybe ints, which is two functors. There's the maybe functor and the list functor. I mean, we have we can of course do we can fmap length over just just one functor. If I do just Haskell, I get just 7. But if I have length nothing, yes, I get nothing. And I of course I can do it for lists. So if I have length Haskell OP, sorry, fmap of course. Length. Okay. But the cool thing now is that it can do these both 2 steps combined. I have both list and maybe are functors. So I can fmap length over list of strings or over maybe strings. But now I can also fmap it over lists of maybe strings. Just 2 examples of functors. Of course, list and maybe is just an example. So it just does, the combination of the 2. It can be any functor. I could also have trees of lists of maybes or something like that. And the fmap just can take such a tower or composition of functors and just works by fmapping. So it can handle these like nested functors. Does that answer the question?
I hope. Yeah. This applying length to a compose.
Yes, exactly.
Yeah.
Compose is just this new, yeah. So basically I'm applying length or I'm fmapping length over a nested functor. It's maybe nested in list. And both list and maybe are functors, so I can fmap over list separately or over maybes, but because this compose of 2 functors is again a functor, I can also fmap over the composition of 2 functors, like a list of maybes, or maybe of lists, or a tree of lists, or a list of trees of maybes, and so on. Okay.
Okay, thanks. Okay.
Welcome. Okay, and same for applicative. So this is also nice, but unfortunately there is no monad instance. Obviously, monad is return and bind, and return is pure. So pure we obviously have. So the problem obviously is bind. You can try to write an instance for bind and see why it doesn't work, but it doesn't. So so the situation for monads is not as nice as for functors and applicatives. So combining monads, given 2 monads, somehow get like a combination of the 2, composition or something, is not as nice as it is for functors and applicatives. Right. Here see a fun example. Just checking. This is just the other way around, basically. Just another example. And the applicative also works. Okay, right. So we can't do this, unfortunately, for monads. It would be nice if we could just use the composition of either string and reader env to get our env air, for example. But we can't, unfortunately, because at least in general, the composition of 2 monads is not, again, a monad. But what we can do is we can define so-called monad transformers. So monad transformer is something that takes an existing monad and produces a new monad. And basically we had this list in the beginning of monads, and most of them have like a transformer version. So instead of the state monad, there is the state monad transformer that takes an existing monad and adds the state effect to it. But I think the running example here is reader. Okay. So we have something, and now I can do this. This is in this MTL package or in transformers package. But let me delete this again. Don't need this. So we have something, it's called reader T. So this is also a naming convention. These transformers normally have a T in the end. So if the monad is called reader, then the transformer is called reader T. monad is called state, the transformer is state T. Like that. There's also maybe T, for example. Okay, so now the state type, the underlying monad. So this is now an arbitrary monad where we try to add the reader effect to it and the result type. And in this case, it's reader T, run reader T. So given an R, produce an MA actually. Right. So that's, I mean, first of all, only a definition. So now the point is, I mean, what we want is if we apply this to a monad M, then we will actually get another monad that has the reader effect. So it's a monad reader. So we can do this, and I think in the slides it's done separately for functor applicative monad, but I think, not sure I really want to do this. I think I just follow the general scheme. So so now we want to like see whether this does any good. So the usual thing. So we need functor reader T R M. Or before I do this, sorry. So if I reload and now ask for the kind of reader T, let's say int. So this is now, or I can of course also ask for the kind of reader T itself. So it's now quite a complicated kind. I mean, maybe the most complicated we have seen so far. So it takes the state type. Then this here, it takes a monad and it produces another monad. Anyway, so let's try to write this instance. Where? Okay, and I need applicative and monad. As I said in the slides, it's a bit more general. So this and this is done by hand, but I don't want to do this. I think it's not worth it in my opinion. So we do our usual thing that we use the boilerplate where we can. And just concentrate on pure and app. So pure given an A. Okay, so the constructor is reader T. And now I must produce something of type R to MA. So given an R, I mean, and the idea, of course, is again for pure that I ignore the power I have now, the state. So I probably don't need this R. Okay, so I have an A and now I must produce an MA. So how on earth am I supposed to do that if I don't know anything about M? Well, I mean, right now I wouldn't be able to. But of course, I mean, verbally, I did say if M is a monad, then this is again a monad. So I will need as a superclass that M is actually a monad. So if I add that here, M, then I know it's a monad, so it's in particular applicative. So I can use pure, which is now the pure from M, and apply it to A. What now? What? Why is this not working? Right. Sorry, because I'm mixing type signatures and implementations. Okay. Right. And actually, I mean, at this point, I mean, I only need pure here. So I could just use applicative, but then I think this would complain. So let me just, and that's different on the slides, but there's more work on the slides. So I keep my life simple. So I just need this monad constraint here and here. Right. And now the interesting thing, as always, is bind. So given something else from reader T RMA and a continuation from A to reader T RMB on the reader T RMB. Okay, so given something and the continuation, so I need a reader T. I have a state. And now I need something of type, I mean, as before, I need something of type MA. And M is a monad, I said. So I can use do notation. I'm now in M. And I mean, this is now do notation in the monad M. I should say do notation in M. Right. So what do I do? I mean, same as I always do. That I also did for the simple reader without T. So I have this M, which is of type reader T RMA. So I can get an A out of that if I run reader T M and give it the state R. So run reader T given this R gives me MA, and because M is monad, I can bind to it. So I get an A out of this. I can apply the continuation to it. Do run reader T on the same state. So it's more or less the same as before for the plain reader, except that now I'm in this monad M. So the whole thing is in monad M. Okay, so this is already nice. So, I mean, given the monad M, I now have this new type reader T, which gives me a new monad. So this is now a way to, given a monad, produce a new monad. And of course, we had to write this code, but of course, in reality, you don't have to write it because it's in the library. And even if you had to write it, you only would need to write it once because, I mean, this is now like a mechanism or like a machine to build new monads. So we have written this instance once, but now you can use it. I mean, you can apply it to all sorts of monads. So this is already cool. But now, of course, the intention is, I mean, and the name as it suggests, reader T, of course, the intention is that it is that this will now be have this reader effect. I mean, that's the whole point why we want this. We want to get the effect of reader T. So the next thing we want is that our, I mean, if M is a monad, that then we have a monad reader, sorry, a monad reader R, reader T, R, M. So we need the ask and the local. So ask must be of type reader T, R, M, R. Okay, and I mean, that's of course very similar. So reader T, given the R, I just turn the R. So it's basically reader T pure. And local, given something from R to R, and something in reader T RMA to reader T RMA. FM, so it's reader T given an R. I just run reader T M on F applied to R. So that's almost like before. Okay, and now I actually have, so now I have a way to take some arbitrary monad M and add the reader effect to it. So for example, the either monad, I mean, we know it's a monad. So now I could, I mean, just as an example, trying to think, did I do anything here? Oh, that was just the check division. Yeah, anyway, let's just take some monad, for example, either, or maybe, maybe,
Maybe.
maybe. So, for example, I can write a computation in maybe something like foo. I mean, it's not important. So, reader T. Let's say the state type is int, and the result type. So the underlying monad is maybe, and the result type is double, whatever. So I can, because I now know this thing is a monad reader, so I can ask for the state. And now, for example, I can do the 1 over this. So I can say when n0 is 0, I do nothing. Okay, and this actually won't work now. First of all, when I have to import from control monad. And in the other case, I do pure 1 over from integral n, right? So now it complains here, right? Because I mean nothing is in maybe, but I'm in reader T. So so actually, and this is a bit silly. So actually, what we want to do, I mean, yeah, I mean, this is good that I try this now. I mean, we can of course do it. Sorry, first of all, I mean, I have 2 nothings there. So, but this also doesn't work because that's the wrong type. I mean, I need something in reader T. So I could of course do reader T. I don't care what the state is, and I just do pure. Sorry, I just do nothing. So this would now compile, but this is like really awkward. Nevertheless, it should work. So let's see. So how can we run that? So want to try foo. So if I do run reader T, foo, and now I must provide it with the state. So for example, 42, and then it gives me just 1 over 42. But if the state is 0, it gives me nothing. Okay, so far, so good. So it works. And I have basically upgraded my maybe monad to also give it this reader effect that I can do ask now. But this is a bit, yes?
I have a question. So if I wanted to use a state monad with, for example, a maybe monad, I will need to write similar instance for that.
I mean, we haven't gotten to state yet, but the same as we have this reader T, there's also a state T transformer defined in the MTL library, or maybe we can also do it as an example. I'm not sure with the time, but yes, in principle, you could also do something like state T, whatever state type maybe, indeed. Yes, so one can. I mean, you have to do these things basically once. I mean, this reader T, I mean, this is like work, of course, But once one has done this work, you can now apply the reader T transformer to every monad and also to another transformer. So, right. I hope, yeah, I'm not sure. Does that answer the question? So one
Yeah.
can do that. Yeah. Okay.
Yeah.
Probably I shouldn't get ahead of myself. So one thing is that this code here that we wrote looks very much like this code here. I mean, the only difference is this one. I mean, the only difference is that it was a bit more complicated because here we were not in this monad M was not there. So here in this code here we had to, sorry, in this one, we always had to take care of the monad M. So we had to like a pure here and do notation here. But in principle, it's very similar. So the good news is actually once you have this reader T, one doesn't need reader anymore. And this is now where identity comes in. So I can just delete all of this. Sorry. And also the instance. And now the idea is to just define reader as, or I can do that maybe, I don't know, here. So reader is now just a type synonym for, so reader R is just a type synonym for reader T R identity. So the underlying monad is the identity monad. This is, I mentioned in the beginning that identity will turn out useful later. So once we have these transformers, I mean, normally there's always pairs. There's like state monad and the state T monad transformer, reader monad and the reader T monad transformer. And the cool thing is that once we have the transformers, we don't need the actual monads anymore because we can just define them as the transformer applied to the identity monad. So now we automatically, because we know reader T applied to every monad is a monad, that is a monad reader. So we now immediately have that reader R is a monad and a monad reader. The only thing that we would like is this run reader, because we only have this run reader T, and run reader is simpler. So given a reader RA and an R gives us an A. And this is now where we basically wrap and unwrap. So we just do the run reader T M applied to R, and now we must this is now does now have the wrong type, I think. I mean, it should have the wrong type. Yes, it does. Because this is now, I mean, it's here we see where's the definition here. So run reader T gives us MA. So M in this case is now identity. So we have an identity A, not an A, but so we have to unwrap identity. This. Okay, so that means we don't have to duplicate work. I mean, we have the work for this reader T to define it, see that it's a monad, see that it's a monad reader. But then reader is very simple. So reader is just the monad transformer reader T applied to identity. And we can write a helper function run reader that we had before using the run reader T and just unwrapping identity. And so that's the one thing. And then the other thing is, this is also not nice here that, I mean, I have the maybe monad, I have combined it with reader, but I would now also like to be able to easily lift something from the maybe monad into this monad, and this is like a bit tedious here. And for that, there is another class. It's called monad trans. And let me just check. I'll go back in a second. Right, this one. So where we have one single method lift, if we have a monad M, then we can take something of type MA and go to type TMA. And now the idea is that we make our reader T also an instance of monad trans. So instance monad trans reader TR where? So we have to implement lift. So that now goes from, if we have monad M, goes from MA to reader TR MA. This is basically what I did here by hand. So lift M is reader T. We ignore the environment and just turn the M. So we can say const M. Right, and now once I have this instance, I can write this here much nicer, just as lift, nothing. Right. So, I mean, so we have these monad transformers. Our first example is this reader T, which now allows us to give an arbitrary monad to get a new monad that has this additional feature that it can read in this case. But of course, I mean, this wouldn't help us if we now basically lose whatever we had in M. I mean, we have effects in M, and of course I mean, by adding this reader effect, we don't want to lose everything that's in there. So and that's where this lift comes in. So with lift, basically we can do everything that we could do before in M. We can also do in reader T R M using lift. Plus we have this additional power now that we can read, that we can ask for the R. So that's the idea of monad transformers. And actually in practice, I mean, it's not uncommon to combine several of them. It's these so-called monad stacks. So in a typical real-world Haskell application, there's a monad stack using, I don't know, 2 or 3 transformers. So you have like a state T, reader T, sep T, whatever. And that's so-called monad stacks to combine different effects. Let me just go back in the slides that I don't forget anything important. Okay, I did this. Monad reader. Okay, so there are other transformers. So we now did this for reader. So as I already mentioned, there's state T, maybe T, except T. So state T is the transformer version of state. So where state was from S to A, comma S, state T goes from S to M of A, comma S, where M is the underlying monad. Maybe T goes to M of maybe A, and except T is basically the transformer for either. So it could also be called either T, but for whatever reason, it's called except T. So it's M of either EA. And then once we have this, basically the actual monads, the plain monads, the non-transformer versions are always just defined as applying the transformer to the identity monad. So we would recover, I mean, either, not in the case of either, because either is so fundamental that it's already defined in the base library, same for maybe. But for state and reader, it is like that. So state is just a synonym for state T as identity. Reader, as I showed you, is just a synonym for reader T R identity. There's also an identity T monad transformer, but that's normally not useful because it doesn't add anything. It basically just makes things more complicated by adding one wrapper. But on the other hand, for the same reason that identity is sometimes useful, like in these cases, this identity T can also be sometimes useful. Right, and now we can do combinations. So for example, let me just, I think I should have a new because I mean, yeah, let me create a new module, because then I can actually use all the stuff from, although no, maybe not, sorry. Not sure now. Yeah, okay, fine. I keep it. Anyway, so we had this example, env_air, and I mean, this is like a we already said it's a combination of reader and either. And if we now squint, sorry, here,
Lars, there,
yeah,
sorry, I have a question. So, do you always need to have a base monad?
yes. I mean, a transformer transforms. It transforms one monad into another. So you need a monad that you want to transform. So we must start somewhere. And yeah, so typically this is either identity or IO actually. Because also like that's not an, I mean, there are these monad transformer versions of, I mean, state maybe except reader, and there are a couple of others monad transformers, but there is no IoT. So you can't add like an IO effect to to a monad. So if you want real world side effects, you basically have no choice but make IO the base monad, the lowest one, and then you apply towers to transformers to IO. But if you are in pure code, so you don't need IO, then normally the base monad is like identity basically. So that's the
Yeah,
most common choices, identity or IO.
yeah.
Okay. Sorry, this is all a bit confusing with the, right. So if we look at this, just remember this env to either string A. And if I now go back to, I mean, that we spent quite a lot of time earlier here when I had this env error to write all these instances here. Env to either string A. But now if we look, oh, sorry, I just see that there's a, oh yeah, because now I don't have the, I don't need this in, oh, just a second. Right, this now doesn't work anymore because now reader is a type synonym, so it's not the constructor anymore. So now I would need to, if I insist on keeping this, I would have to write reader T and reader T, and now it's identity. No. What is it? Why not? Just a second. Constructor identity was not in scope. I just want to fix this now. I mean, this gets now more complicated. But as I said, that I mean, we don't use that anyway. That was just an example for these associated type families. So now I have run reader T M FR. Okay. So now I think everything hopefully compiles again. I think. No, it doesn't. No. Yes. Okay. Everything compiles again. Right. And if we look at this env_r, it was env to either string A. And if we look at our reader T, that has this shape. For R equals env and M is either string, which means I wouldn't have to go through all this trouble. I could, so this is all not necessary. At least this is not. This is now complaining, of course, because it's not a monad. So let me just, for the time being, right. So instead of doing this, we could have just defined type nr is reader T. Env is the state type, and the monad is either. So the old one was this. Sorry, either is not a monad, either string. Right, and then we also don't need this instance because we have that for free. We know that reader T always is a reader instance. Okay. So this is one example how one of the monads that we as an example is just now an application of the reader T monad transformer. I think on the slides there are other examples. Okay, so this is okay, and fine. I mean, instead of either, I could also use except T string identity. I mean, this is, yeah, whatever. And we had this one from your homework, this error state. So this is now a combination of the state monad and either. So we could write it as state T with state type S. And again, either string or except T string identity. So basically, I mean, if you had known that before, then you wouldn't have need to go through the trouble of writing the monad instances by hand. Same, our parser. So this is now not either, it's list. So it's again reader monad, so reader T, no, sorry, state monad, because we can update the token stream. We consume tokens during parsing, but now it's not in the either string monad, it's in the list monad. So parser could just have been defined as state T, where the state type is token lists, and the underlying monad is list. Right. And there's also actually a list T I mean, so list can of course be the base monad because I mean these transformers work for any monad as base monad. But the question of course is there also a list T monad transformer that basically adds indeterminism to an arbitrary monad? And the answer is yes, there is. But there is like the traditional historical list T, which is in the MTL package, is actually broken. So that is not the correct implementation. However, there are other packages on Hackage. Maybe we can look at one like in the next lecture or so that do that properly. So in principle, there is a list T, or there are several implementations of a list T monad transformer that add non-determinism to an arbitrary monad. And of course, we can build on top of I/O, as I just said. So then in that case, the base monad is I/O. So we could, for example, have like read from environment, like a configuration, and be able to throw like pure exceptions of type message, but underlying have real world side effects. Okay. And there is no transformer version of I/O. So I/O is special in that regard. If you want I/O in your monad stack, then it must be the base monad. Okay. And right, I mean, they use this example, but I think we just use another one because we already have that. Let's go back to the examples. What examples did I have? For example, this one here. I mean, I did this when n equals 0, lift nothing. But I also wrote this instance earlier for monad error maybe, right? That this one. So the maybe monad is actually an instance of monad error. So if I combine, like in this example here, if I combine the reader T effect with the maybe monad, I should also get an instance of monad error because of maybe. So instead of doing this lift nothing, I mean, in a like just word, I should be able to say throw error unit. And maybe I am. No, I'm not, because now the compiler complains that I don't have a monad error instance for reader T and maybe. So even though maybe had this instance, this somehow gets lost when I apply the reader T transformer to it. I mean, there's no reason why it should still be possible. However, we can implement one. So we can say instance, if we have a monad error EM, and now that we then also have monad error E of reader TRM, where right. Okay, and I think we should be able to write this. In,
String, maybe there.
did I? Okay, there's the one instance. Where's the definition? Here. No. Let's see. But I did give the functional dependency. Let me just check on the slides whether that's exactly what I want to write, right? So must be a mistake somewhere. I need some using undecidable instances must help. There's also a tip somewhere in the slides. It's another extension, and I think that fixes this. And there's a remark in this. Yeah, okay, fine. There's a remark in the slides that it sounds bad. I mean, undecidable instances sounds like a dangerous extension, but it's actually harmless. I also don't know exactly what it does. But I mean, normally the compiler gives this hint, and then you can just add it. Okay, so now of course okay, fine. This is now, let me just fix the problems that we have. Because now I defined that differently. I mean, this is now defined, env error is now defined as, what was it? Reader T. I mean, this is now a bit silly, but so given env right, and local is now reader T env run reader T. So see whether this is okay. Okay, fine. So now, of course, I must implement this. So I have throw error and catch error. So throw error. So E to reader TRM. And this is now actually easy because I have this lift. So I know how to throw errors in M. So I can just lift that. So I can just lift throw error E. Yeah, A. Okay, so this is simple. And often when you do something like this, it is as simple as this. The catch is somewhat of an exception. The catch is a bit trickier, but basically that's as tricky as it gets. So reader TRMA and a handler from E to reader TRMA go to reader TRMA. So let's see whether we can do this. Catch error M handler. So it's reader T given an R to redo. So we can catch error in the underlying monad, suppose. I suppose we have to. So catch error run reader T reader T M R. Let's check. Okay, fine. And this is now from E to MA. Okay, fine. And it's now the handler. So if we have an error, so I must now, of course, use the given handler, but that gives me a reader T. So I must do run reader T given handler applied to the error message and the given state. Okay, this is basically the same instance I wrote. I think I wrote that. It looks very familiar. Yeah, I deleted that now, I think. This one, exactly. This is basically exactly that. So that's now also no longer necessary. Right, and now this example, this foo compiles again. So so now I know that if I have a monad error before, then applying the reader T transformer doesn't destroy this. I mean, this is important, right? The goal that we have is we have these effects. So we can have the throw and catch exception effect. We have the mutable state effect. We have the indeterminism effect. We have the immutable read-only state effect and several more maybe. And we would like for a real-world application or for our application, we want to combine those effects. And we know, so we looked at the example of reader. So all the other things like state and accept work very similar. And we saw the reader T monad transformer is indeed a monad transformer. So it transforms one monad into another. That's already good. And it indeed adds the reader effect. So if we have some arbitrary monad M, then reader TM is actually a monad reader. So we now have a way to add the reader effect. But of course, it wouldn't help if we, by adding one effect, destroy another effect. And this is an example here. So if the underlying monad had the monad error effect, then by adding reader T, we still have the monad error effect. And typically, this is relatively easy to write. So this is more typical, actually, that you just need lift and more or less just lift. Catch is, because catch has a complicated signature, catch is a bit trickier. Right. But this also shows one of the problems with this approach. So, I mean, if you want to, I mean, there's this handful of classes. So, I mean, there are these effects. Like I said, we have reader, we have state, we have, let's say, just reader, state, and error. I mean, those three are actually the most important ones, and maybe monad IO. So we have, let's say, these three effects. So now we write transformer versions for them. Fine. So then, of course, we first must show that the transformer actually gives us this effect. Okay. But now we need these compatibilities so that we don't, by applying a transformer, don't destroy an existing effect. So now basically for every combination of effects, we have to write an instance like this. So, I mean, we also would need the same for the state T transformer, that if we start with a monad error, state T of M is again monad error. We would need it for the except T transformer and so on. I mean, not that because that's already monad error. But anyway, so the point is, each time in this MTL monad transformer library that is very popular in Haskell, in the Haskell community, each time somebody wants to add a new effect, you basically have to write instances for all existing effects, that the new effect is compatible with the existing effects. So in that sense, it's quadratic. I mean, that's like people call it that, I think, the quadratic problem. So each time, I mean, you introduce a new effect, you basically, in the library, you have to like write more and more instances to make it compatible with all existing effects. On the other hand, that sounds worse than it it sounds worse than it is because there are not that many effects. I mean, in principle, reader, state, and error are the most important ones. And I mean, those instances have been written in the MTL library, so that's all good. So you don't have to do anything there. So it's actually not that bad. Nevertheless, let me just see. So we do this here. I mean, I could do the same for monad state. So same that if the underlying monad already had monad state, then reader T doesn't destroy that. And in this case, you see it's very simple actually. So actually with this lift, which is introduced here, one can do this very quickly. Right. There are also actually monad transformer laws, so that lift plays nice with return and bind. So if you lift a return, it's the same as return. And you lift a bind, it's the same as first lifting the parts and then binding. So yeah, also what one would expect. And let me just see, that's what I just said. So lifting is actually quite trivial. I mean, normally it's trivial. If once you have lift, writing these instances is very easy. Right, but it can be tricky, but that's only for cases like catch error. Catch error is somehow special. And I think this is in principle the lecture. But I mean, we still have some time, so I think we should have maybe another break. And then there's at least one thing I definitely want to show you that's important, that the order matters. But let's just do this last slide. Just let me see whether I forgot something. So the point of monad transformers is it allows you to build new monads out of existing monads. And you can and that's a way to combine effects, like having state or having exceptions. So basically you pick your effects and then you just go to the MTL library and check the monad transformers and then apply different monad transformers. And unfortunately, I mean, it's not very elegant. So it's not as nice as it would be for functors or applicative. So, right. And somehow the Haskell community is still struggling to find the best way to do this. So the traditional way are these monad transformers. And I mean, I think they work well enough actually. But I mean, in Haskell, people always strive to find the right way to do things, even if it takes decades to come up with the right way. So people are, still experimenting with different ways of doing this. There's also something called effect systems, which is a different way of doing this. So there's a part of the community that believes that's the right way. And incidentally, in Plutus or in Cardano, I mean, like in the beginning, when you wanted to do off-chain code for Plutus and you wanted to use the IOG libraries for that, they made heavy use of something called effect systems, which is like an alternative to transformers. But luckily, those days are behind us, so now it's much, much easier to work with these things. Anyway, so I think we should have a break, maybe at 1/4 past, and then I want to at least show you an example of combining different or that order matters, that actually the order in which you apply monad transformers can make a difference, because that is like an important topic. Okay, but let's have a break until 1/4 past, okay? And
Yeah.
then we can do that. Thank you.
Okay.
Okay. Okay, I'm back. Should we continue?
Yeah.
Okay, now maybe I do take a new, because I did lots of ad hoc stuff here. Let me just create a new module. And let's call it order. Let me delete all of this again. And let me update the Cabal file. Let me reload. Okay. There's one remark in the slide. I'm not sure whether I've done that already. So order matters. So some of these monad transformers, I mean, of course it matters. I mean, it's obvious from the definitions. That's the difference whether you do reader T, state T, or state T, reader T. But for some of these combinations, even though it's like syntactically different, it behaves the same. So there is no semantic difference. So it doesn't, I mean, if you want to combine two effects, sometimes it doesn't matter in which order you apply the transformers, but sometimes it does matter. I mean, reader tends to be very harmless in that regard. It basically doesn't matter where in your transformer stack you add reader. But state and exception, for example, they are like my favorite example for where it does matter. So let's look at an example. Okay, and let's say we first we don't even know what monad we have. We just know basically what instances we have. So let's say we have, I don't know, doesn't matter. Bar. So if we have a monad, let's say we have a monad, we can throw exceptions of type string, and we have mutable state of type, let's say int. And of course, I must import those things. Now I imported from the MTL library. So monad state is defined here. And monad error is in monad except. I mean, this is correct, but nevertheless, to make it more uniform, let's import it from there. Right. So of course, that's not complete. So if I have such a monad, I have, like, let's say, a computation of type M double. Bar do. Okay, what do? I first get the state. Then maybe I increment it by 1. Then, so this I can do because I have the monad state constraint. I have get and put. And now if n is 0, now I make use of the monad error constraint. So I throw position 0. And otherwise I return as before. I mean, this example from integral n. What's the problem now? Okay, I need some of these extensions again. And I think when is not in scope. So let's import this. Right. And maybe I can do a bus. Same constraints. But now double bus. I just do this twice. So okay. So far, so good. So I mean, I can write code against these abstract interfaces. So I just know I have some monad that where I have error in state, and then I can write this code. So the idea is, I mean, I look up my state, I increment my state by 1. If the state was 0, I throw an exception. Otherwise, I return the reciprocal value of that. And in bus, I just do this twice and return the pair of reciprocals. So now I have, like, I want to try that out. So I need a concrete monad that actually implements these two things. So and obviously, I mean, we know now we have like a state monad transformer and except T monad transformer. So there are at least two choices. I mean, I can use, for example, either string as a base monad and then apply the state T transformer to it, or I can use state as a base monad and apply the except T transformer to it. So let's start with 1, and let's just M1, so write type synonym. So it doesn't matter which way. So I don't know. Let's start with state T int applied to the either string monad. I need to import this. Okay. And it's also always useful, I mean, and I think there will also be homework for that, or at least, yeah, whatever. I mean, once you have these relatively complicated monads, you always need like a way to actually run them or execute them. So that I always call it runner. So let's call it run M1. So given something, and I need an initial state. So int is my state. And what will the result be? Let's see. I mean, okay, before I do this, why not order? Was it order? Yeah, order. Okay, so state T is S to M A comma S. So I have something of, so before I write the signature, let me just write it. So I get something of type state T and I get an initial state N. So what do I do? I mean, in order to run this state T thing, I can do run state T. And I must give it the state T computation, the M, and I must give it the initial state. And then luckily it already gives me this. Okay, and so what's M in our case? M is either string. So I have either string. And what's S? S is int. Right. And I mean, of course, I actually wouldn't need to. Does that work? It's a bit. Oh yeah, sorry. M1. No. Oh yeah, the S is an int. Sorry. Int. Sorry. Got confused. Like this. Right. So it's just run state. But I mean, sometimes there are like several layers. So maybe we can have, if we still have time, we can have an additional example with 2 transformers to make that clearer. Okay. And now I mean, I can try this out. So run M1, my bus. Let's say if the initial state is 2. Okay, so I get right, so no exception. And now I get a pair, so it's 1/2 and 1/3. And the new state is 4. So the original state was 2. I do bar twice, so I increment it twice, so the new state is 4. And I do the reciprocals of 2 and 3. So fine. And now, of course, the interesting case is if I encounter a 0 on the way, which I do if I start with -1 or with 0. So let's start with -1. And I just get left division by 0. So far, so good. But now, I mean, we have an alternative, right? We can do it the other way around. And if I do type M2, so I do except T string applied to the state int monad. And now I need some more imports. So now, how do I execute something there? So I have my run M2. So if I have an M, so I have an M. So what do I do? So now it's an except T. So I have this run except T of M. Just a second. We asked for the type. Why not pray? Oh, I didn't save. Okay. Sorry, I thought it's called run except T. But I do import it. What's the problem now? Oh yeah, no.
The root, because it's SFT only.
I'm sorry. Let me just. Yeah, sorry. Let me just comment it quickly. So what's except T? Okay, that doesn't have a run. Fine. So for some reason, it's a bit inconsistent. I mean, it should, so it doesn't use this record syntax for new type. Fine. So I don't have that. So I must pattern match. So I have except TM. So that is now of this type, M either EA, and M is now the state monad. So this M here is of type state int either EA. So in order to, so now I have to run state without T, because this is now M is the state monad, not a monad transformer. M initial state, which I must also give, of course. And the run state is not in scope. Okay. Now I can give the type. So, and this looks horrible, but this is just my M2. State is int. And eta reduce. What's now? Yeah, is string. Okay. Right. And actually I should just sort that differently. And now we see that, I mean, we do get different stuff, right? I mean, we can, let's first see that whether it works. So, I mean, I can reload, and now I can do run M2 on bus 2. I get basically the same result as I got before. I mean, when I did the run M1, it looked very similar. So I mean, I get 1/2 and 1/3, and the new state is 4. So this is like very similar. But now recall what happened if I ran it with -1 with our old runner. I just got the error message, division by 0. But if I now do the run M2, I also get the error message, but I also get the state, the original state at the time when the error happened, actually. Or actually the update, yeah, exactly. So the original state was, Right, that's interesting. I even get the final state. So I mean it starts at -1 and then bar is called twice. So I get all the state updates until the final state 1, and just the result, of course, is division by 0. So they really behave differently. So in this order, in the first order, if it's state t applied to either, if it fails, I mean, and you also see that at the result types. So here in the first case, the result type is either string a comma int. So in the failure case, in the left case, all I get is the error message. I don't get a result and I don't get some state. Whereas in the second combination, if it's this way around, I mean, in the success case, I basically always get the same. I get my a and a new int. So here as well in the success, but here we see I always get a state, and then I get either a result or an error message, but always a state. It's a pair of an either and an int, whereas here it's an either of a string and a pair where the int is in. So they behave differently. This M1 monad in the case of failure basically forgets the state, and the M2 monad in the case of failure does not. So even though the result is gone, it still has the state. And it's not to say, I mean, one can't say that one is better than the other or worse. It really depends on what you want to do. So I mean, in some applications, basically, I mean, especially if you want to catch errors, I mean, of course, we could also try to catch them. I mean, sometimes you basically want to be able to continue or want to still have the state update, and in others you don't. So the point of this example is mostly to make you aware of that even though, I mean, that the order matters. So depending on what result type you want, in this case, for example, I mean, it would would make a difference how do you order them. And especially, I mean, either or except and state T are definitely examples where order matters. And as I said before, reader T, I think is less critical. There it doesn't really matter where you put that. And maybe I should have one. I mean, there are actually several examples I can think of. I mean, we could do like, and because in reality, there are often more than one transformers. So maybe let's do that. Yeah, let's do reader, accept, and list, for example, just as a second example, also with these run functions. So let's say you want, let's first write another function. Let's call it I don't know, Kuba, bus, what else? Doesn't matter. Let's call it Nairobi. So let's say we have monad error, whatever, maybe a string again. Or no, let's not do it like this. Let's do it concretely. So let's say now I want I want lists. I mean indeterminism, but I also want to read from some integer configuration, and I want to be able to throw string exceptions. So for example, I can do except t string, reader t int, list. Right. Why is this now giving me grief? Okay, fine. And reader I must import. Okay, reader T. Right. So, I mean, this is something you might see in a typical application, so that people stack several of these transformers on top of each other. So you want exceptions and you want read-only state, for example. And now I can write an application. Let's say, can I think of something? List is a bit unusual. Doesn't need to make sense. I just try to think of, yeah, whatever. I mean, let's start by asking for the state. And then what can I do? For example, I can do I don't know. I can divide 10 by it and 20 or something. I mean, or add 1 and divide 10 by it. So I can do and I mean, the add 1 is of course unproblematic. Oh yeah, and it's supposed to be supposed to be of type M, let's say double. Okay, fine. And okay, again, if it's 0, I throw an exception. Division by 0. And then I can, so now I want to also make use of this list so that I have indeterminism. So I lift because it's 2 layers down. I think, and now I do whatever, 1 over from integral n, and can also do a let. Double is from integral n. Okay. I must import the monad reader class. Okay, and I must import monad trans. For example, I can get that from monad reader. Okay, fine. Let me first see whether it works. Oh, no, I can't, because this is the point. We want to write a runner. But first, I mean, why I can write it like this. So I have applied 2 monad transformers, except T and reader T. Except T gives me monad error, so I can in particular do throw error. And reader T gives me ask, so I can ask for the read-only state. And then finally this thing here. So I have at the bottom, I have my list monad, and then I have 2 transformers on top of it. So by doing lift twice, I can lift something from the int monad up into my M monad. So lift, and then it's double, but I mean, I have indeterminism, so I give a list of doubles here. So that works. I mean, I can write it, but now we somehow want to run it. So we want something like run M. So given the computation in this monad, and I will need an initial state, and let's see what we get. So first of all, the whole thing is an except T as before. And for some reason, I still can't fathom there is no run except T. So I must pattern match on it. Okay, so now what? So now this M is of type, we had that before. out again. So this is now of type M, either EA. So M is now the rest of this transformer. So it's this thing. So in order to make progress now, to unpeel the reader transformer, I must do run reader. On this M thing, and the initial state var N. Okay. And what do I get? So let's see. First I can eta reduce. Okay. So I have my M, some result type. My state type is int. And M is list. The error type is string. Okay, also interesting. So now I can try this. And if I first do it far away from 0, so Nairobi 5 or whatever. Okay, then both succeed. I mean, it's indeterminate. So I get a list, but no errors occur in each of these options. I get 1/5 and 1 + 5. Now, of course, if I do it with 0, I get this error division by 0. And this is something you typically, I mean, in real world applications, I mean, typically you pick your monad stack, it's called, so which transformers apply. And then often you have something like this run function, which then depends on exactly what, I mean, what transformers you use to take something from your application. And then sometimes, I mean, if you use state or reader, you will need to apply an initial state. And then the result type again depends on the things you did. Right. Are there any questions at this point?
No questions so far.
Okay, good. And right, then maybe I just give one more example, just an example where we just, yeah, we still have 10 minutes or so. Right, can do this. I hope. Just 1 second. Do you remember by any chance any of these that had I think concurrency? I always forget. I can never write these stanzas by hand. So let me just copy an existing one. Just wanted to executable, whatever, more monads. Main is more monads. I don't need anything except the library I'm writing, more monads. And okay, don't need all this. Fine. And let me just add one more reader IO, let's call it. Right, now don't want to, let's be quick. So first I this, then I copy source order to source reader IO. Okay, I reload. Come on. Let me close this. Let me close this and this. And open that. Reader IO. Okay, and now it will probably complain because the main, yeah. So the main program that I now added, just need to do a main function. Oh, and first, don't do anything here. Okay, just to get it compiled. As I said before, it's always a good idea if everything compiles every time or all the time, then it's much easier. Right, so I wanted to show you a very common combination of use case for monad transformers. Some people in the community even say it's basically the only thing you should do. And that's the combination of reader T and IO. So let's define type M as reader T config. I'll define config in a second. Or for simplicity, let's say the config is just a file path, and as underlying monad we use IO. So of course I have to import this again. So this is very common, reader T over IO. And it's often used, as I said before, for like config files. And when I talked about readers, I tried to come up with an example with these significant digits, but that was a bit forced. I mean, because I didn't have monad transformers then, so I couldn't use this. So here it's much more obvious. And okay, we again want a runner, of course. So let's call it run M. So that will get something type MA and a file path in this case, and it will be IOA, and it's just run reader T. I mean, I could just use run reader T. I prefer to hide this, but I mean, anyway. Okay. And right, and now we could do something like log. So it gets a log is unfortunately this for logarithm is already used. So let's call it write log. String to M unit. So we can do write log message do. And now because M is a reader T, I can do ask. So I can ask for the log file. Let's say the meaning of this configuration is the log file position. So do ask. Now, what was it with file? No, it's not. That's the wrong one. What is it? System IO. What's the signature again? Okay, it takes the path and the mode, and then it gives me a handle. Fine. So let's use okay, the path is the one I just asked for, and what's the okay, ask is not in scope. Must first get that. Okay, fine. Just for a second. I think I need IO mode. Let's forget. Isn't it called IO mode? Okay, sorry. Right. Let's use append mode for, I mean, for a log file that seems appropriate. Okay, now I get this handle, and then I can just do a age put string line age message. Lots of errors. Okay, fine. Is that also here? H put string line, yeah. What else? Okay, it seems there is some append file functionality. Fine. You could use that. Whatever. Now, what's the error? Ah, right. Okay, exactly. I mean, this is something that lives in IO, but I'm not in IO. I'm in reader T IO. And I showed you these classes earlier. And for IO, I mean, we could do lift. So I could just do lift. But specifically for if IO is involved, there's maybe I should just do lift. Right, so this would work. But actually, in this case, if IO is, we saw earlier in my previous example with the lists, we saw that I had to do lift to get it all the way up. And of course, the same would happen to IO if it's like deep in the stack. And for that purpose, there's this monad IO class that I showed on the slides earlier with something called lift IO. And that basically, if IO is anywhere in your stack, it gets it all the way up. So I probably should use that. Now it's complaining that I have lots of redundant inputs. Fine. Okay. So this is very simple, write log. And now I could do something. I mean, typical application now would be, let's do whatever. Example proc or something. Type M unit, let's say. Do maybe get line or something. I mean, I can now ask for things. It doesn't matter. I mean, I can just do something arbitrary for M 100. Say live write log O N. Okay. Okay, fine. I mean, it's boring, but anyway. So I have this now. And now how you would typically use this in a real world application is something like, so first of all, I need to import this reader IO. And secondly, something like system.environment get args to get access to command line parameters. And then I would do something like do log file get args. And now I can do run m example proc log file. Right. Should hopefully compile. Right. So I mean, so that's like how a lot of real-world Haskell problems are structured. So right in the beginning, you somehow read your configuration. I mean, I now do it from the command line parameters, but of course you could also read it from a config file or whatever environment variable or so on. And then you basically your actual application is defined in some sort of monad that has a reader T part where you pass in this configuration. So in this example, the log file is the configuration. And then basically, once you work in this M monad here, then you always have access to this configuration, so for example, the write log function was able to ask for it. That can be arbitrarily deeply nested in your code, and your code is not polluted by everywhere carrying this configuration around. But when you need it, you can just ask for it. And now let's see whether it actually works. So I can now do cabal run. What was it called? More monads. And now as command line argument, for example, test.log. Okay, now hopefully there's a test file now. There it is. And it indeed contains the numbers from 1 to 100. So yeah.
Yeah, cool.
So it works. Thank you. Yeah, this is typical. I mean, this is a very typical. I mean, normally it's more complicated because you want other effects maybe, but I mean, this is like a very common pattern. It's called the reader. I think it's called the reader IO pattern or something, or reader TIO. So to have a reader T transformer over IO for your actual application that needs to do stuff in the real world. Okay, are there any questions? Otherwise, I'm done for today.
Yeah, I think. No question.
Okay, then thank you very much for your attention and have a nice weekend and talk to you on Monday. And thank you very much.
Thank you. Bye.
Thank you. Bye.
Bye.
Bye.